So in this video I just want to extend our knowledge of integrals involving trigonometry. And let's just begin with a review of what we know so far in terms of basic integrals. The integral of sine is negative cos. The integral of cos is sine, because the derivative of sine is cos. Okay. Now in terms of the integral of tan x, I don't actually know this at the moment. So I need to find out what that is. So I'm going to write tan as sine over cos. And then I'm going to do an integration by substitution, and I'm going to use u to be cosine x. The derivative of cos, doing derivatives over here, is negative sine x isolating for dx so that I can substitute it into here. So I'm going to get sine x over u times du times negative sine x. And I did that because the signs cancel out, and I now have negative integral of 1 over u du, which is one of my basic integral formulas. It's negative ln, absolute value u, plus c. And if I plug my u back in here, it's then negative ln cosine x plus c. And it would be fine to leave the integral of tangent that way. But we could also bring the negative exponent up, negative in front up as an exponent. And so I would get ln absolute cosine of x to the negative 1, which is the reciprocal of cos, which is secant. And this is typically the formula we use for the integral of tan, is the ln of absolute value secant. Okay, this integral doesn't come up a lot, but you should know what it is, or at least know how to develop it should it come up. And without going through this entire process for cotan, it would work similarly. The integral for that turns out to be the ln of absolute sine x plus c. Alright, so I'm sure you're wondering then, well, what about the integral of secant and the integral of cosecant? Because we don't yet know those either. So, this one's a little bit more complicated, and here's how the argument goes. I am going to take my secant x, and I'm going to multiply top and bottom by secant x plus tan x. Okay, that expression in blue is obviously 1, so we can do that. Now I'm going to expand out on the top to get secant squared x plus secant x times tangent x, all divided by secant x plus tangent x. How is this ever going to work out to be something nice? Alright, so we're going to do an integration by substitution, and we're going to pick a u so that the derivative of our u is another part of the integrand. Forgot my dx here. There we go. So if I pick u to be the bottom, you might see ahead that the derivatives of these will be what we have in the numerator of the integrand. So du dx equals, okay, back to derivatives here. Interesting how integration by substitution involves differentiation and anti-differentiation. Derivative of secant is secant times tangent. Derivative of tangent is secant squared. And so dx isolated is du over secant x tan x plus secant squared x. So putting all this together, we have the integral of secant x dx to be the integral of, okay, that over u. Okay, so let me squeeze that in. Times dx, which is this. And those cross out. And so I have the integral of du over u, which is the ln of absolute value u plus c, which equals the ln of absolute value u secant x plus tan x plus c. And similarly, if we did the integral of cosecant x dx, we would have gotten a similar expression, this time ln absolute cosecant x minus cotangent x plus c. So now I want to extend the inverse trig integrals, which there are three important ones, and make them just a little bit more general. We know this integral, the inverse sine x1, and what I want to do to make this a little bit more general is, what would I do if instead of having 1 minus x squared I had just a general number minus x squared. Alright, so as we do with anything that's similar to what we know, we change this into the form of what we know and then work from there. So I want to basically make a 1 there. So I'm going to do that by factoring out 1 over root a squared and because this is a constant, it can be pulled out front, and since a is a positive value, that will simply be 1 over a integral 1 over the root of 1 minus, I'm going to make this x over a in brackets squared. I'm doing that because I'm setting myself up here for an integration by substitution. So if u was x over a, du dx would be 1 over a. Isolating for dx, I would get dx to be a times du. Doing my substitution back, 1 over a integral 1 over root 1 minus u squared times dx, which is a times du. Turns out after all that, these a's cancel out, and I've got a basic integral here, which is inverse sine u plus c. And substituting back then, that would mean that my integral that I started with is equal to inverse sine u, which is x over a, plus c. Okay, there it is, nicely put together. And if I were to apply that to an example, let's suppose this one, I would recognize, hopefully, that the integral is of the form 1 over a squared minus x squared, and so it would be inverse sine of x over a plus c. Now, what if it was even more complex than that? What if we had the following? So I've now got this set up as the integral of 1 over the root of 2 squared minus, this would have to be 3x in brackets squared dx. And I would then have to do an integration by substitution, using my u to be 3x. The derivative of that is 3, isolating dx, substituting, integral 1 over root 2 squared minus u squared times dx, which is du over 3. It's 1/3 which is 1/3, and this is inverse sine u over a plus c, which is equal to 1/3 inverse sine 3x over 2 plus constant of integration. Alright, what happens on this integral when we change the 1 into an a squared? We're keeping a positive, remember? Alright, so again we're going to change this into the form of this. And we'll do that by factoring out 1 over a squared. And I'm going to write it this way because I know it's probably going to go similar to the last one. And now I'm going to do an integration by substitution again. So u is x over a, which means du is 1 over a dx, which means dx is a times du. Doing my substitution, that's going to become 1 over a squared integral 1 over 1 plus u squared times dx to be a times du. So this time we have only one of the a's canceling out, and so it becomes 1 over a, and the integral of this would be inverse tangent u plus c. And so putting it all together nicely, our new expanded inverse trig integral is 1 over a inverse tan of u, which was x over a plus c. Okay, so unlike the inverse sine one, this one has a 1 over a in front of it to begin with. And the final inverse trig integral that we know is this one, and we want to extend that so that the 1 is an a squared. And I'll just bypass the proof this time and tell you that it turns out to be this. So just update your 3 inverse trig integrals to include a fact that we can have an a squared in place of the 1.